Alright, draft physics video. Yeah, I hit the button a little too soon. So I want to adjust these settings. Speed this up a little bit. I'll start it back in the beginning. Usually YouTube fucks that up a little bit. So anyway, we're going to do this relativity stuff. What the hell? Because in my opinion, this is something that maybe is provable. We can actually find evidence and demonstrate it in a few different ways, and to prove that the premises of general relativity are, well, really it's supposed to be, it started with special relativity, is just nonsense. This idea that you can give forces momentum in two dimensions, two directions. The forces all move the speed of light in one dimension. That means they can only move in one dimension. They can only go one way, the speed of light. They can't go the way, the speed of light, and also go some other direction. They can't carry momentum. I've sort of made this argument. So it sort of has to do with how you basically think about what matter is. And I've sort of explained that matter can move in three dimensions because it's like it has three gyroscopes, or however you want to look at it. It has pieces in it that will allow it to exchange force. So force can come in this way, it can collect it on this in this dimension. Force can come in this way, it can collect it on this dimension. Force can go this way and collect it on this dimension. So it can trap force in three dimensions. That is, it can have actual imbalances in force in actually all three dimensions. It could have some imbalance this way, it can have some imbalance this way, and it can have some imbalance this way. All at once. And so it'll move some diagonal of that. In the sense the matter will work it out. And that's how it can exist, is imbalanced. It can possess imbalance. And that's the nature of velocity for material things that have three dimensions that you can add to and subtract from. Photons are one-dimensional. That means they can't trap anything. They can't hold energy. They're not batteries. Matter is a battery. It collects energy with momentum. This doesn't. A photon can't collect energy in any momentum. It's always going the speed of light, and it's always in one direction. Can't go in two directions at once, either as a wave packet or as a ton, as I would call it. So as an elemental bit, it can't carry two dimensions. Can't carry two momentums. Certainly can't carry three dimensions of momentum. So the illustration is kind of obvious. So Hoffaday argues that it can, that it's just like a piece of matter. So a piece of matter, I put it on a train, the matter acquires the acceleration first. First it has to be accelerated, and then it maintains a velocity with the train. And that if I throw it off the train, there's no reason it loses that velocity unless I throw it off the train with the opposite force. So until the equal and opposite force happens, matter will continue to do what it's doing. So that's like a Newton law. It maintains the velocity until a force takes it away. Forces can't act on a photon. Photon is force. So forces can't stop a force. Matter has to stop a force. And so there's no matter stopping it. It goes the speed of light in one direction, one dimension, period, nothing else. It can't carry momentum. So what argument to make first? I'll just point out how this is the argument being made. So this is the 60 symbols video. I'll also play this. And somebody's responding to their animation. They asked the question the wrong way, but anyway, the guy answers this way. Light consists of photons, which, if the spaceship is already moving, have an inertial velocity. So the claim is that the photons have velocity, not just going the speed of light in a direction, but they have velocities in two other dimensions also. So the photon not only is going the speed of light in this direction, but it can go 50 miles an hour this way, and it can go 70 miles an hour this way. So it can have 3 velocities in the direction in which the spaceship is moving. So he's claiming that the photons actually do move in 2 directions. They're both moving the speed of light in one direction plus some sideways motion. If you think of photons as basketballs, basketballs are matter. Let's understand. You should say baseballs because basketballs are actually, they don't exactly function quite as well because of their mass to volume ratio. Anyway, it's like throwing a basketball up in the air while being on a moving bus. The ball doesn't fall behind. It does lag a little bit actually because it's full of air. But anyway, yeah, so that's a material thing. Material things collect velocity through acceleration. Photons are never accelerated. They have the same acceleration they're born with as this acceleration will die with. They don't ever accelerate. They are always at speed, and they only have one speed. Now, this clearly, that in my opinion is glaringly wrong. You can't give a photon 2 momentums. You can't give it 3 momentums. Can't do that. And the paradoxes it creates, as I've pointed out or tried to explain, is that, well, you can create faster than light communication if you're allowed to give extra momentums. So I'll make a little illustration of a scenario, a possible scenario, and I'll show you the implications of this rubbish. So say you're here in space and you want to communicate with somebody here in space. So there's clearly a distance between you, and the light will travel the speed of light to communicate, and that distance will take a certain amount of time. Now if you can accelerate this, okay, source, in the sense that this little packet of photons, you can move it real quickly. Like I take a magnet and I move it really quick. Then the last little bit of magnetism, where I stop, that last little bit will jolt past the magnet and can affect some wire or something. That's what they're arguing. The magnetism carries the momentum of the velocity, the acceleration, and the acceleration continues in the sense that that's the direction the magnetism will travel. Is now it will travel in the direction of the movement, which is, in my opinion, nonsense. And I'll illustrate in this argument. So here's the paradox. Say if I want to travel this distance, okay, so you see that length of that line. The trick is if I can give light 2 momentums, that is if light has inertia from wherever you're moving when you emit the light, then all I really have to do is move the source of the light, the thing emitting the light. I move it in this direction. And if I move it in this direction, it'll continue to move in that direction. So, and I'll do it for free. So, let's say I can move it 1/4 of the speed of light. That might be this distance, but anyway, let's just say this is the distance I have to travel to do what I'm arguing. So my argument is there's 2 difference. You can look at this as being 2 directions. You have this distance between the 2 objects, and you have this distance. Now if I can use momentum to get rid of this one, so both of these will be traveled at the same time. So let's understand that their argument is when the light's emitted, it's going the speed of light this way, and it's going the speed of the ship this way. So this direction is completely free because it happens at the same time as this movement. So it's doing both at the same time. So they don't have to do both. It doesn't have to do an Elysing thing. It does them both at the same time. So they're both accomplished within the same amount of time. So this is like free movement. So the trick would be is move this fast enough, and then your photon will travel this way as it's traveling this way. And you will actually be able to shorten the distance between here and here to this distance. So you will be able to communicate with this other person faster than the speed of light by whatever this comes out to, maybe 30%, maybe 25%. So 25% increase in communication time faster than the speed of regular light. Regular light would require you to do this, but because you're going to send the light perpendicular and you're going to give it an extra momentum going this way, you'll be able to shorten the distance to this distance. Because by the time it gets here, it's not going to take any more time than it takes to get to here. So say if you can get those photons moving really quickly, get the jiggle really fast, the pulse, make the pulse really fast, like 3/4 of the speed of light, then all you'll have to travel is this distance, because the photon will do this distance for free. So I claim the patent on faster than light communication by their theory. So if what they're saying is true, I claim the patent on faster than light communication because I can see it's kind of obvious how to do it. Just shoot light out of moving things. Just jiggle things when you shoot the light out. Move it really fast. So basically I could take something, and I don't have to move it distance, I just have to move it quickly for each pulse. So I could just have to go quickly this way and have a pulse of light. And then pulse a little bit of light, doing that again, move the thing back, and then pulse again, and then pulse again. And as long as I move it really quick when the pulse happens, that pulse will continue to move with the velocity I give it, plus move the speed of light in the direction I want to go. So all I have to do is shoot all my light perpendicular and just make sure I shoot it out of something moving very fast. And I can guarantee myself faster than light communication. So that's the consequence. That's the paradox created by this nonsense. There's lots of other paradoxes, but I'm just saying that's the obvious one, is that you've now created a means for making light go faster because you can make it go two ways at once. It can go two directions at the same time. And if you use 3, it's more complex math, where you take this angle also, what would be drawn as that angle, you can increase it even more because you can shorten your distance by another 1/4. So you can theoretically communicate half the speed of light. So twice as fast as the speed of light. Half the amount of time required to cover the distance. Alright, so to play first. I guess we'll do the 60 symbols video first because it has the animation in it. The all-important animation. So let me just draw my animation again, just so we understand what we're talking about. So you have a spaceship going half the speed of C in this direction. We have a light emitter that's a laser, and it shoots perpendicular to a hole in the side of the ship. So when the ship's not moving, the light goes straight across, goes through the hole, and out into space at the speed of light. And when the ship is moving, they're arguing it's doing the same thing, which is, in my opinion, nonsense. That nothing changed. So the not moving state is exactly the same as the moving state. Yeah, so it's not even that you can't tell the difference between, your relative movement. You can't tell the difference between any kind of movement at all, which is, in my opinion, just again nonsense. Because light's a force. It's not matter. Yes, if I'm standing here with my little boots stuck to the floor, I'm moving with the ship because I'm matter. I can have velocities in different directions. All the physical material things will move with the ship. The forces will not. They're not obliged to have 2 velocities. They can't have them. So anyway, the theory is that obviously at half the speed of light, this is 4 feet across. The argument is by the time this ship moves 4 feet, this light has moved halfway across this distance. It's half the speed of light, right? Yes. And so at that point, this hole has, in that same amount of time, it has moved 2 feet. So it's 2 feet away. Well, it'll be 2 feet away by the time the full 4 feet goes. So by the time this is halfway, this will be 1 foot away. So this will be 1 foot in half the distance. So at half the speed of light would be 1 foot here, would be where the hole has moved. So by the time when the photon left, it's going straight, and now the hole's over here. And by the time the photon would get to the other side, the hole would be over here. And their claim is that no, the photon has both velocities. So it moves this way. So it not only moves the speed, moves c this way, and plus it moves half c this way. So it does both of these momentums. So it really travels this diagonal line, and therefore it will be able to go through this hole over here. That's what they claim happens. So it shoots out perpendicular, but it's not really going perpendicular because it's going to move. For every step it takes this way, it takes a half a step this way. So every step forward, one step, half a step sideways. So every time it goes forward, it goes half a step sideways. That's their claim. They claim that's what light packets and that's what photons do. They carry more than one momentum. And if I was clever enough to give this spaceship a third momentum, that is, it's moving this way and then I nudge it this way with rockets on the side, so now it's going two ways, I can do that even more complexly, and still play this game like it's going to go through a hole in the side of the ship. Alright, yeah, so I'll play this 60 symbols one first. So I'm just saying this is just absolute misunderstanding of forces and the difference between force and matter. Forces, the stuff moving the speed of light, is not matter. Matter, it functions differently, and it gains velocity. The environment gives it velocity. Forces are not given velocity by the environment. They always have the velocity. When they're inside your matter, they still have their velocity. The force always has velocity. It's always moving. And you can't give it velocity, you can't take its velocity away. And they think, because I'm in a special frame of some kind, okay, I can break the rules of physics, and now I can give light momentum. And again, another one of the consequences of this is that if you were looking at planets in the sky, and you have to understand you're looking at their perpendicular full face. So we're not talking about you being able to see some angle. We're talking about them looking full face at you. So the light comes off of the full face of, say, a moon or a planet, and you see a round, full moon. Their argument is that, let's say the moon was much further away, and it took, say, 3 minutes for the light to get to the moon. The argument would be, okay, is that as the light left the moon, it's on its way, and this is where it's going to go. It's going to head for you as the observer. And that's the location that the light's going to hit. And it's going to take 3 minutes for that light to get there. And in that 3 minutes, the moon will have moved to over here, let's say. And again, it's going to have the same, these are usually round patterns, but we're looking at the same face. So there's the same face at the same distance. And so in 3 minutes, the moon moved to here, and to see the full moon from here. So their argument is that the light from this moon, okay, from the past, continued to move on this trajectory. So it maintained the inertia. I don't know which inertia, the acceleration from gravity or the acceleration of the moon. See, the moon has two velocities. It has the velocity going this way, and it has the velocity going this way. And those are combined into this pattern. And so matter can do that. It can combine two velocities. But this, well, one's an acceleration and one's a velocity. Let's be clear about that. So the argument would be that this velocity, okay, is the one it's going to keep. So the light is all moving this way. Okay, so it has the momentum of the moon. So the light will end up, the photons will end up moving in this direction plus the direction towards the observer because it's perpendicular. So these are the two vectors that will be combined, and the photons will end up on a pattern where you'll see it there. So you won't see it at its current position because you can't see the acceleration. The acceleration won't be part of what happens to this photon, but its inertial velocity will be maintained. So when you look at the past, you're neither seeing where the moon was, like so if we look at Venus in the sky, or Saturn, if you could see it as a dot, you know it's the right dot. the truth is you're not seeing Saturn where it was, and you're not seeing Saturn where it is. You're seeing Saturn at some point that it never was and never is, because the light will effectively look like it's coming from this angle, because by the time the photons get to you, they'll move those two directions. So they'll start off here, they'll go this way, they'll go this way, they'll go this way, they'll go this way, and it'll end up looking like it's coming from there. Alright, so that's another one of these paradoxes. So there's just this glaring flaw in this 60 symbols animation, again, where they don't explain how this is possible at all. They don't cover the idea of light carrying two momentums. So they just create this light clock, and that's all you get, is just the image of the light clock. So I'll go back to his talking about it. And so I took the mirror out because, yeah, it makes this example so much more obvious.
Get to gamma. To do that, we have to think about clocks, because clocks are one of the things that get affected by traveling close to the speed of light, that time slows down. And of course, if time slows...
No, see, it's not just clocks. Everything gets affected by the speed of light. Everything material, traveling fast. Gaining force screws with your matter. It means that your matter can't be doing what it was doing before, because now it has to spend quite a bit of time doing the mechanical process of being moved. So I've given the example, I'll do it again. If I ask you to dance as fast as you can, matter is always working as fast as it can. It never does anything slower or faster. It always is functioning at one speed, as fast as it can. And so if matter is functioning, and then I say to the matter, well, dance. Okay, so you're dancing as fast as you can, and then I ask you to move sideways. You'll notice that you can't dance as fast, because you have to take time out to keep moving one step over, and that time out, okay, inhibits your ability to do your dance steps. Well, the same thing happens to matter. So the metabolism of the matter slows down when it's forced to keep moving the elements of the matter in a direction.
Down, that means the speed at which clocks are going is going to change, but everything's going to change. The speed at which radioactive decay occurs, the speed at which you age, everything is going to change. Just because if they didn't...
Okay, let's also understand when he says change, this idea of slowing down and stuff, no, it could change in all kinds of radical ways, and there's points where it won't change in any kind of proportional way. It'll just change in a way that completely breaks the functionality, and the mechanism will never work again. It won't be able to produce the same kind of radiation. It won't be able to function because it'll lose it's losing its function. It's not doing it all proportionally. It's doing it in ways that will eventually break it, and it won't function as matter anymore.
It all changed together, then you'd know there was something funny going on, that suddenly, I'm only living 15 years instead of 75 years, and therefore clearly something's changed with the laws of physics. So any clock you choose to use...
Right, so their premise is because Einstein said so, and because they said fine, they have a rule now. It's a law of physics that there can't be any indication that could give you a clue that you're actually moving. They just say that's the way the universe works. You can never know that you're moving because there's no way to test for your movement. And they just claim it as an absolute fact. Now the only evidence of that they have is they go on a train going 40 miles an hour, and they say, look, my saucer doesn't fly off the table, nothing's happening, everything's moving 40 miles an hour, so therefore everybody just adapts to whatever speed I'm going and everything stays the same. But yeah, that's not an experiment at anything close to the real speeds that we're talking that force moves at. So it's not relevant to experiments with the speed of light. And light doesn't obey these rules. It doesn't carry your inertial velocity.
All other clocks.
If you shoot light in front of you, it doesn't move faster. If you shoot light behind you, it doesn't move slower. And if you shoot it sideways, it likewise does not carry your inertial frame. It doesn't care what your frame is.
Clocks have to mimic its behavior. So in special relativity, when you want to derive this equation, you can kind of set up a rather special kind of clock, a thing called a light clock. And so instead of having a pendulum that ticks backwards and forwards, 1 tick per second, what you actually have is, you imagine you have a light source and a mirror. And what you do is you fire out a burst of light that goes up, hits the mirror, bounces back.
Right, you have absolutely no reason to do the bounces back part. You could put the sensor on the other side, but then the problem is you can never receive the signal from the sensor because it takes more than the speed of light time for the signal from the sensor to even get back to the signal. So, there's no way to actually build a clock that could tell time with this mechanism, even telling time with this mechanism. So it doesn't even work in that theoretical sense. You'd have to have the emitter and the receiver have to be both at the same length of wire to some sort of central processor. So they didn't even bother with those details. So again, all I've done is get rid of the mirror and just have a hole that the light goes through or doesn't go through. That's it. Simple. Hit the button, Gary.
Comes back, and then you've got a little detector next to the mirror which says whenever I detect some light, I'm going to send out another burst of light. So really you've just got little bursts of light going backwards and forwards. And it's just like a pendulum clock in that sense, that actually it's sort of ticking backwards and forwards between there. And so you could use that to measure time. It's not a very sensible way to measure time, but it's a perfectly good way of measuring time. And whatever time you measure with this light clock has to be the same as what you'd measure with your pendulum clock or your radioactive decay or whatever it is.
Right, so that's if you wanted to measure time. And there's no reason to measure the time, in my opinion. It's of little or no value. So you don't need a clock. What you need to know is, are you moving?
Alright, so now we need to think about what happens to such a clock. So let me draw a picture of it. So here we've got our light source, we've got a mirror up here, and we've got a little detector here. So in simple terms, all you're doing is you're firing some light up there, it bounces back, and gets detected.
Alright, so just understand, they're just going to keep the light doing exactly like this isn't moving. They're just saying and if I move all of these parts, I move the mirror, I move the detector, I move the emitter, the light will also move with everything. So the light will also just carry the momentum of the train. Every photon released will go both ways. It will go the way this way and it will go that way. That's their argument, and I say it's overtly silly.
And then you've got a little thing that says, okay, whenever I detect some light, I'll send another pulse up, backwards and forwards between these two. And we'll make this distance a distance h. And if our clock's ticking, supposing its period is tau, so it takes a time tau to go from there to there and a time tau from there to go from there to there. So that's analogous to like 1 second on a pendulum clock, because a pendulum actually only completes a period every 2 seconds. Right? It goes one way for a second and then the other way for a second. So this is going to be a clock. It's probably, we make it, the trouble is if we wanted it to be a second between ticks, this thing would have to be 300,000 kilometers.
Right, so he didn't, he bothers with this kind of technicality, but he doesn't get to the technicality at all of saying that, well, now I'm going to move this emitter and I'm going to pretend that each one of these photons sits there and actually moves into the future to hit the mirror where it's moved to, and then come back down to hit the emitter where it's moved to. Oops, wrong button. Yeah, sorry. Gotta learn how to... well, I gotta pull the keyboard out. That's what I gotta do.
Totally practical. So it's probably going to have a shorter tick, but we can write tau if we want. That h, in terms of the period, is c times tau. So basically it's tau to get from there to there, tau to come back again, just like from a pendulum clock, 1 second to tick one way, 1 second to top. And that's what would happen, if I had one of these clocks sitting next to me, or, if I was sitting in a rocket and I had one of these clocks along for the ride with me, that's what I'd see. But now imagine I'm watching somebody in a rocket.
Right, okay, so now he just said he would have this clock next to him in a rocket, say moving half the speed of light, and this light beam would just keep going up and down, just like he wasn't moving. It would just maintain my velocity. It would carry two velocities. It would go the speed of light up and down, and it would go half the speed of light in that direction. It would carry two velocities. That's what he's saying.
So I'm not moving. The rocket is moving relative to me, and they've got one of these clocks. And so they're watching it going tick-tock.
Right, so he's claiming that light carries the momentum of the ship. So each photon, once emitted, is not only going the speed of light this way, it's going half the speed of light this way. And that's okay with you clowns. I mean idiots. I mean fools. I mean retards.
Behaving in the way that we've just derived here. From the perspective of the person in the rocket, they're just seeing the light going up and down, but of course the rocket...
Right, so I'm claiming clearly that won't happen, okay? That will never happen. The photons will go up, And as they go up, the ship moves out of the way. It hits the mirror way back here. And then the light goes back down here, and there's no detector because the detector took the fuck off. It's gone. It's in the future. No chance whatsoever. The photon does not carry two momentums.
It, from our perspective, is moving along, which means that the mirror is moving along and the light source is moving along, which...
Okay, now the light source is moving along, which means... Now, if he's going to say the magic words here, I'll be quite surprised, but it sounds like he's going to say them.
The light, instead of going up and down like that, is actually going like this, from our perspective.
Right, okay, so there we go. From our perspective. Now, I don't know whose perspective he's talking about. From our perspective in the ship, or from our perspective looking at the ship, but either way, the point is he's saying the light carries two momentums. And he'll show it in the image like it's going backwards, as the viewer would see it. But what he's really saying is, no, the light goes forward with the ship. It carries two momentums.
Then coming down again. So if I just draw that, what's happening is from the, the light's emitted at some point, and from our perspective we're seeing this whole thing moving to the right, so actually what we see the light doing is instead of going straight up, we see the light heading off in this direction.
There we go. Okay, so there we go. He look how they did this line. I don't even understand how they could even do that way. Okay, so the photon left here, he's saying that the photon carries the momentum of the ship and the speed of light this way. So it's carrying two momentums. This distance is still the same distance this way, so it still only takes it the speed of light to travel this extra distance, because they're saying this is free. This was all free. So my point is that technically you can use this mechanism to shorten the distance between any 2 points in the universe, and always shorten the distance of the communication to the length between where your future source is. Okay, so let's play it some more.
Hitting the mirror, as the mirror's moved to the right by the time it hits it, and then coming back down again, and of course by the time it gets back down to the detector again, the detector's moved to the right again.
Right, okay, so this is what they say light will do. Light carries two momentums, or three momentums, just like matter. So light, a force, behaves just like matter, which is matter, is a complex three-dimensional object. So a one-dimensional object is capable of absorbing 3 dimensions worth of velocity. It can carry velocity in more than one dimension. I think that's just preposterous. Idiotic, moronic, silly. No evidence that force can do that.
And so the light, instead of going straight up and down, follows a path like that. So it has further to go. From our perspective, that light's gone further. But also, the speed of light is the same in every reference frame.
Right, so it's gone further, but the speed of light is the same, but it can't be both. So that's a contradiction right there.
And so the light's got further to go, and it's travelling at the same speed, so therefore it takes longer to do it. So one of those ticks in our reference frame takes longer than it did in the reference frame in which the clock was stationary, just because...
Right, okay, so that's his argument, is that it actually does take longer for the light to get to the other point. So even though there's only one part of the velocity that should be counted, which is the speed of light going this way. So let's draw that. They're saying the light's moving 2 directions, this way and this way. Well, we know this distance is always the same distance. I mean, this distance is a distance. To get from here to here is a distance. Okay, the light is traveling c going this distance. And now they're saying, okay, that the light is actually traveling this path, all right, to get to the hole in the future. So it moves this path to get to the hole in the future, and they're admitting that's a further distance. And they're saying that now the light takes longer to do this perpendicular thing, go straight across, because it's actually moving in this direction. So now they're counting this extra velocity this way as actually consuming time, that it actually consumed time to go this way. So somehow the light didn't do both at the same time. It did this for a little while going the speed of light, and then it stopped. And then it went this way for a little while, and then it stopped, and then it went this way a little while, and then it stopped, and then it went this way a little while, and it stopped. So that's sort of the implications of what they're saying. If it takes longer to get to the hole, then I don't know, he's saying it takes longer, and yet at the same time, I'm just trying to think if there's some other way to verify that in terms of what the logical statement is, in terms of, well, there's got to be a way of detecting how long it takes light to go a distance. I mean, it doesn't get through obviously it's not going to get to the hole in the same amount of time as the original distance. So again, so they are counting both. So they are counting both velocities as consuming time. So the real path was actually the light travels this length, and then it travels this length. So it travels those two lengths, which means it takes it longer to get to the other side. Which I just say it's just nonsense. So all this is just premised on thought experiments. There's no physical evidence that any of this bullshit happens, that light goes forward. Okay, so just understand what they're saying. I shoot light perpendicular, the light actually moves forward. So that's what they're saying. I can't shoot perpendicular light in a moving object. It won't go straight across. It won't go perpendicular. So that's all I need is a square. So Hoffaday showed the square. Let's see. Still not going to help in this circumstance, because they're going to keep claiming that it defeats the square, because the square will be in the future also, and so from the future's perspective it went straight. So he's going to claim that you'll see the light go in the spaceship, you'll see the light just go straight right across, and outside the spaceship you'll see the light go forward into the hole. But then which one of these comes out of the spaceship? Which way is the light moving when it comes out of the hole? Is it moving this way, or is it moving this way? I guess that would be the next question to ask. And I guess somehow they're going to pervert it into like, no, it comes out of the hole perpendicular to the ship. So this is just such bullshit. Alright, so I might as well play the end of this since I started it.
The light's got further to go, and therefore it's going to take longer to do it. And we can fairly straightforwardly mathematically figure out how much longer it's going to take to do it. So let's go back to the picture again for a second. So this is still this distant h. That hasn't changed, which we've already said is equal to c times tau. That hasn't changed. That's our ticks that it would be. The light is now moving at the speed of light c.
Well, see, this is c. We know it isn't c times t, it's c. We know this is moving the speed of light. And so the light moving in this direction, the speed of light. And he's just saying, no, the light moved this direction, the speed of light. But it didn't, again, where's the evidence that the light didn't go straight? Why wouldn't the light go straight? Why does the light go forward? How does the light know to go forward?
You see it moving, and it's going to take us some time t to get where it's going. So the distance the light's travelled along here is the speed of light times how long it takes to get there, c times t. Right? And then remember, this thing is moving to the right. It's moving to...
Well, there's very little point in doing c times t. Well, they use tau. Okay. Different t.
the right at some speed v.
Right, so the photon is moving that way with the emitter. So it goes with it. So it's just like a baseball off a train. So that's their claim. So if I want to hit a sign, if I go on a quick train, and I want to hit a sign that's coming, because the laser is going to have momentum forward, I have to shoot behind to actually hit it where I see it. So if I aim right at it, I'll miss, because my laser is going to shoot forward all the time. So I'm always going to have to shoot behind things with my laser, because my laser is always going to shoot crooked. No matter where I point it, it's always going to go crooked. Is that the theory?
Which means by the time the light has got to the top here, this thing will have moved the distance over here. How far will it move? Well, if it's moving at speed v and it's got a time t to do it, then the distance it travels is just v times t. And this is just a right angle triangle we've got here. And so we can apply Pythagoras' theorem, which says that the hypotenuse squared is equal to the sum of the squares on the other two sides. So ct squared is equal to c tau.
Right, and you'll get whatever I said, 20% or some kind of, it'll be a figure like that.
Squared plus vt squared. So let's just write that down. We've got c squared t squared because we squared the whole.
Well, you didn't use real numbers, so what's the point? Well, anyway, it's almost over.
C squared tau squared plus v squared t squared. Now I need to do a little bit of magic to rearrange this formula. T squared is equal to tau squared over 1 minus v squared over c squared. And then I just take the square root of both sides. That tells me that the time I measure in my reference frame is the time you measure in the reference frame in which the clock is stationary, divided by, now I've got to take the square root of the bit on the bottom, 1 minus v squared over c squared, which is just gamma that we defined before, times tau. So the factor of gamma is how much time gets changed by, how much time gets multiplied by. So this is saying that the time we measure, t, is related to the time in the reference frame in which the clock is stationary, so the thing called the proper time, by some factor.
Yeah, so from some factor. So each bit of velocity is really just saying, okay, we're going to add this extra bit. So we're gonna combine the two. So the normal speed of light is this, and because we're moving the source, now the real speed of light is going to be this angle, so this line. So any movement that the original light has, so any movement I give the laser moving is going to be counted as more time, as it's going to consume the time that the light's actually moving the distance. So it'll all end up, so yes, you can't go faster than the speed of light because they're actually saying the light carries the two momentums, as unlike the real world where material objects don't do that. Material objects don't take time to do both velocities. The Earth does both the acceleration in towards the sun and its own velocity. It does them both at the same time. It doesn't take the Earth extra long amount of time to travel those two, to combine those two. Yeah, there's no extra consumption of time. Alright, so that's probably enough of that. Then we just do the holiday thing. I don't know what you want, cat. I gave you food and specials and all kinds of good stuff. Alright, so let's have Hoffman. They have his spiel. But anyway, I think this is theory. There's no logic to this theory that you can give 3 velocities to a photon, that you can have it move the speed of light in the direction it's going, and to give it another velocity, and give it another velocity. That you can give a photon 3 velocities. No chance. Yeah, you suck at juggling.
Anywho,
I can juggle much better than
here I am, travelling through space at 1,000 miles an hour. And you know what? I didn't have to think about throwing each of those objects ahead of time, because I'll be over here. Yeah? The reason is momentum conservation.
Right, so again, he's saying that photons have momentum, not in the direction the photon's moving, the speed of light, but it has momentum sideways. It carries sideways momentum. So, again, if I have a laser beam and I'm going on a very fast spaceship and I want to hit a target, I can't aim at the target. I have to aim way behind it because my laser beam's going to shoot crooked.
Linear momentum conservation in this instance. Well, actually, this kind. For our purposes, it's linear. Now, the fact of linear energy conservation comes from Noether's theorem.
Right, so they're going to talk about matter. He's going to talk about matter, and we're talking about forces. So again, show me where I can take a magnet, move it really quick, and that the last little bit of magnetism will move forward. And so I can impart electricity into a wire that I don't have to actually go perpendicular to. I can just throw the magnetism at the wire. That's your fucking idiotic theory.
And it's a mathematical theorem, in fact. If you want to say, hey...
It's not. I mean, again, there's no fact based anywhere. There's not one piece of factual evidence demonstrating that you ever have moved a photon in 2 dimensions?
You know what? I think physics over there is the same as physics over here. Boom. Guess what you get?
Well, that's not what we're talking about. We're not talking about physics over here and over there. We're talking about physics on things moving half the speed of light.
You get from that symmetry, not picture symmetry. Mathematical symmetry is about operations, and in this sense it's about translational symmetry. The physics here is the same as the physics over there. From that fact.
Right, and I would argue that this is true in the sense that the photons don't care about whether you're going 10 miles an hour or you're going 1,000,000 miles an hour or 1,000,000 miles an hour. The photon's always going to go the speed of light in the direction it was initiated in. It's not going to move in 2 dimensions. It's going to go the speed of light one way for a solid object in the future. I mean, I've sort of made this point, but at the time of emission, as soon as you emit a photon, regardless of what your spaceship is doing, your photon has a direction. And there's a point in space it's heading for, a solid point in space. So when the photon is initiated, it has a solid point in space that it's heading right for. And it's going the speed of light for that solid point in space. And you can't say, no, we're going to keep changing that point in space. We're going to keep making it change that point in space. So we're going to say the photon's here, it's moving to this point in space. And when it's here, it's moving to this point in space. And when it's here, it's moving to this point in space. Different points in space. No, it was moving towards one point of space, and that's where it goes in a straight line. Feynman said that photons move from point A to point B in a straight line. They don't go from point A to B, then they switch to C, and then they switch to D, and then they switch to E, and then they switch to F. They don't do that.
I presumed. Run it through Emmy Noether's thinking, for pure logic and greatness, and you get boom, momentum conservation.
Alright, so again, just totally trivial, and so he's saying photons don't have what you call momentum conservation in the direction they're actually moving the speed of light in. They have momentum conservation in the direction they're not moving the speed of light in. So it moves c this way, it moves half c this way, and then it goes this way in some magical bullshit scenario that doesn't happen because photons don't do that. Homie, photons aren't baseballs off a train.
And if similar kind of idea with rotational symmetry. If you say, you know what? When I do physics with my clock, and I say, right, reset, okay, and I time an event, and I go reset 0, and, oh, do 10 seconds. Now, if I want to do another experiment, the question is for the numbers to work out in the equation, do I have to? What happens if I forget to reset? And I go from 10 seconds and stop the next one, and it's now reading 15 seconds. That only took 5 seconds. Oh my God! Oh, it's all over! Yeah? No. The physics of now is the physics of now.
I don't know how this relates to anything, but what is this about?
So it has to have that time translational symmetry. And all you have to do is put T2 minus T1, and it all just works out into the equations.
So again, they're arguing that the conservative view, the conservation view, is to say that you can give light forward momentum, inertia, you can give it momentum. Besides the direction it's going in, you can give it some other momentum. And I don't know how exactly would you take that momentum away again? So you gave it 2 momentums. How do you get rid of that second momentum? What does the photon do to get rid of that second momentum? So it's moving the speed of light this way, and you're basically saying that means it can hit something going this way. So, because does that make any sense to anybody? You can take away its momentum by having it crash into something going the way it's not really going. Oh.
So, you've had this explained, right? I think I'm throwing it up. The laser light, you think the laser light is going across, or going to try to go across, linear momentum conservation, as I said it would be braking. You could fire lasers out the side, and it would slow.
Well, look, this whole stupid firing lasers out the side. I mean, the amount of laser you'd have to shoot out the side to slow down your matter. I mean, we're back to the E equals mc squared. E equals m times the speed of light squared. So I don't know what kind of lasers you're talking about firing, but they're going to have to be like really high wattage to equal mc squared.
You down, right? That was the implication, but straight over to people's heads. Right? Just think about it. Ask yourself, does your forward velocity decrease if you shoot laser out? And
yeah, if you shoot enough of it, yeah, of course it does. Because you're letting loose forward force. Then that's the opposite reaction is going to be, you're going to go more the other way. So you're going to lose acceleration. You're going to decelerate.
And it does what you say, right? So if imagine making that flashlight. It doesn't have to be a laser, it's just light shining, yeah? And you get piece lumps of your spacecraft and you convert it to energy and you shine a little torch, yeah? And you pick off bits. In the end, yeah, the physics says when your spaceship's gone and you're just in your suit because you've converted it all into to energy and shined a flashlight.
Well, again, so this is a tremendous amount of energy. Let's, again, nuclear bomb kind of energy he's talking about. So I've reduced the matter into, I've produced a nuclear bomb worth of energy forward of me, and I'm surprised that I stopped moving? No, I don't think I'm surprised.
Physics says you'll still be flying at whatever, quarter the speed of light, half the speed of light, 90% the speed of light. You're still flying that speed. The tactic of throwing things off the side, yeah, was not ever going to slow you down. In fact, the only way would be to, I guess, throw things directly in opposition.
Well, isn't that what we just talked about, is throwing stuff in opposition? I mean, obviously, throwing stuff out the side isn't going to change. Getting rid of the sideways force, the perpendicular force, isn't going to change anything. It's just, unless you imbalance it, then it'll drift you in a direction. But I don't understand the point of this whole argument. I mean, he obviously doesn't understand three-dimensional motion.
In fact, if he was throwing things off and they fell behind and they was doing that, he'd probably, not if he was exactly, he wouldn't do anything, but it would certainly, and that might be the way anyway, move you to the side. So look up. I've just done. There's some good like hour-long videos on them, but there's a little channel called the Science Asylum. This theorem explained. That's Noether.
There's just no point. Again, we're not talking about matter. We're talking about a force. You're saying a force can have three velocities. It can move in 3 dimensions. Well, Maxwell's equations doesn't say it can do that.
Notice theorem about this time symmetry. If you want to have the physics over here and the physics over there the same, then you have to have linear momentum conservation.
Well, again, linear momentum conservation. So we're not talking about the conservation of the speed of light in this direction. We're talking about this conservation of the momentum of the light in some other direction, not in the direction it's traveling.
If you've got linear momentum conservation, Leonard Susskind once said that's equivalent to saying if you want to juggle on a train, you don't have to learn anew. Yeah, once you've learned it.
Right. So we're just using material examples to describe a force. So you're saying that light carries your momentum. Again, you're just saying that I can give light 2 velocities. A velocity going that way and a velocity that way. I can have a photon of light go the speed of light that way and half the speed of light that way.
Juggle on stationary land, you can juggle on a moving train, no problem. There's no thinking required. Yeah, all you have to do is think you're throwing it up. Yeah.
Yeah, they're all matter. They're 3-dimensional pieces of matter. Matter acquires velocity. Photons do not. They don't slow down, they don't speed up, and they definitely don't do 2 different directions at the same time.
And the universe conspires to make sure that it gets that the direction you think you're throwing it is an apparent direction. Yeah, it will always retain that automatic throwing ahead, or is it throwing behind? Yeah, it'll be throwing ahead to arrive there.
Yeah, right. And again, through what physical mechanism? You're just basically saying that Maxwell's full of shit, and you're saying that you can move a force in two directions, and that I can shoot a laser light out of here, and it won't go straight. It will, in fact, go crooked. And the faster I move it, the more crooked it gets. So if I move it 99% the speed of light this way, I can force the light to come out of the laser perpendicular to the laser. Bullshit. Fucking bullshit. Silly bullshit.
Yeah, the universe conspires to take care of that for you.
Well, whatever. You claim it. You got no facts to base it on. Not one shred of a fact, anywhere near a fact. Show me a force moving two directions at once. Go ahead. Show it to me. Show me a magnet that I move the magnet really fast, and the last bit of magnetism overshoots, goes forward. Show me where that happens. Show me a laser where if I move it really fast this way, the light ends up going this way and that way. Go ahead and show me that. Show me proof that if I took a laser beam and precisely had it on a machine that just moved it sideways, back and forth really fast, that the laser light ends up coming out this way and that way. Go ahead. Show me proof. Evidence. Show me a laser on the outside of an F-15 and the laser light shoots forward. Show me. Full of shit. People are full of shit. I'm just saying, look, you know, you don't. I don't know what to tell you, but yeah, I mean, if physics is this stupid, if it doesn't understand that a photon's a one-dimensional object, and that it can't carry velocities, it does one thing: it moves the speed of light in one direction. It doesn't obey any of these momentum rules because it doesn't slow down. It doesn't speed up. It goes one speed. It has nothing to do with material velocity. Matter is made out of force, going in all directions, in all the dimensions. The three dimensions, all directions in the three dimensions. That's what matter is made out of. So you can give it a little extra this way, and give it more that way, and give it all kinds of extra velocities, and that it can carry those. But a photon can't carry this, the speed of light, and this, half the speed of light. Can't do it.